All right, guys. So today we're going to be talking about the stiffness matrix again. And what we're trying to point out is, based on the previous lectures that we posted online, this one is important to identify exactly why do we use a direct stiffness matrix. Basically, with the direct stiffness matrix, we are able to analyze frames and find out the deformations. We were not able to do that with statics course or mechanics of materials or structure analysis. We are basically trying to get the deformations that we're having at that structure, the support deformation here, and the deflection shape. And then the forces, both shear, moment, and normal force within this frame. We are also able to analyze trusses, whether they are statically indeterminate or statically determined, whether they are internally statically indeterminate or not. We find out the deformations, which is a major thing. We find out the support reactions, and we find out the member forces, as you can see right here. So the method that we're having is called the direct stiffness matrix, and basically, in order for us to establish this direct stiffness matrix or the stiffness matrix of the whole structure, we are going to go through certain steps. So bear with me that we are going to isolate a member out of the structure, as you can see right here, hold the far end and call it a pin support, or put a pin support right here, and the near end is going to be free. And then we apply a certain force that is producing a unit displacement right there, and then find out exactly what the stiffness is, or what is the relationship between the force that's developed at the far near end and far end because of the unit deformation right here. And this is the equation that I'm talking to you about. Q sub n prime, that is the force that's developed at the near end due to the unit load right here. AE over L times D sub n. Where are we getting this equation from? If you remember from this mechanics of materials course, we said that the deformation equals PL over EA. If you just like tweak that equation, you will find out that the force equals to a certain term multiplied by deformation. That term right here is nothing but the stiffness, which is AE over L. That is the force developed at the near end, as you can see. And the other one is the force developed at the far end. It's the same exactly like that one, AE over A times D, but the sign itself is different. And the negative sign, that means that the force is acting opposite to the positive direction of X prime. So what we're doing now is trying to establish the stiffness matrix for that member along something called local axis, X prime and Y prime. It can be represented as such with that box here at the top, or it can be represented as the one here at the bottom. Either you say Qn prime, or you can say Q11 and Q21. And we are going to tell you what does mean. It means as first subscripts showing you the location at which the force is acting. The second subscript is designating that the deformation at the first node. That is very clear right here. So I'm exactly copying from this member to that member and just telling you that this first element right here, which is Qn prime, is the same as Q11. What does that mean? The first subscript denotes the force that's developed at force 1, at node 1. And the second subscripts denote and identify that the deformation at the near end. How about here? Q21. It means that the force developed at the second node or the far node. Due to what? Due to the deformation 1 that is at the near end. Repeat the same process by switching the support. So instead of holding this as pin, we hold the other end, which is the near end. So here we go. We hold the near end at the pin support, and we apply a unit displacement at the far end and figure out the relationship that we're having between the force and the deformation, as you can see here. Force equals to an entity or a term multiplied by deformation. What is that term? It is K prime, or the stiffness in the local coordinate axis. So we have the force that's developed here at the far end and force that's developed at the near end. If you are stretching this member in that direction, then definitely the reaction is going to be opposite to it. And then look at it. Is this force in the positive direction of x prime or negative? It's opposite. So that will give us negative value. How about this force at the far end? Is it in the same direction of x prime or opposite? It is in the same direction. That gives you positive value right here. So from this, you can figure out, again, that stiffness matrix in the local coordinate, as you can see. When you combine them both, so now we have superposition so that we can have both cases at the near end, at the far end. So we have dn, which is at the near end, and d far at the far end. When you combine both, you will find out that the q sub n, which is the force developed at the near end due to the deformations, both of them, is going to have two terms, ae over L times d sub n, and negative ae over L times df. What does that mean? That means that there is a force developed at the near end due to two things. One of them is deformation, unit deformation along the, or at the near end, and another unit deformation at the far end. Both of them combined will give you that first term right there. For the second one, which is what is the force developed at the far end, something like here, what is the force developed here? Due to unit deformation at the first node or the near end, and unit deformation at the far end or node 2, that is going to give you this equation right here. You can write it down this way, or you can write it down this way. Q sub n is nothing but Q11 and Q12. It gives you these two terms. I'm just copying what we have here and there. With that being said, now we do have a relationship between the forces developed at the near end and the forces developed at the far end due to this deformations. So we come up with that load displacement relationship or equation in a matrix format. So I have a vector which has Qn and Q far, which means that the force developed at the near end and the force developed at the far end. And I have in the right-hand side another vector that is identifying d sub n and d sub f, which is nothing but the deformation at the near end and the far end. The relationship in between is this stiffness matrix as we had before, which is ae over L times 1, negative 1, negative 1, and 1. So that K prime, as you can see here, is the stiffness matrix of the member in the local coordinates. And that follows and abide by that law that we had in physics and we had in strength of materials, that the force equals to stiffness multiplied by the deformation. Can we notice something here? It's a square matrix. That's number one. The second thing is that along the diagonal here, you will have positive values right there. And as you can see here, the Kij prime is having force at joint I due to displacement at joint J. So Kij prime is telling you that the force developed at joint I due to a displacement at joint J. And this is going to give you an idea of this matrix. What does that first column mean, or what does the second column mean? The second column, which has K12 and K22, as you can see right there, represent the forces in the member only when the far end or node 2 experience a unit displacement. Again, the second column in this matrix represents the effect or the forces developed due to a unit displacement at the far end. So just keep this in mind. With that, we are done with the first step. What is the first step? Identifying the stiffness matrix of a truss member in the local coordinate system, which is x prime and y prime. Again, we are rewriting this equation and saying that if I equals 1 and j equals 1, that tells you that the force developed at the near end due to a unit displacement at the near end of 1. If we're talking about that, then we end up with this equation right here, which is K11 prime. If we're saying what is K21 prime, in that case, we are talking about the force developed at, was it the near or the far? K2, at the far end. And then the subscript 1 denotes what? It's identifying that there is a unit displacement at the near end. Here we go. These are the two systems that we had, and this is the final shape that we have. And with that, we complete the first step, which is identifying the stiffness matrix in the local coordinate system. And as we talked earlier, that the diagonal is going to be positive, and it is a square matrix, as you can see it. But in reality, after you develop all this stiffness matrix, in reality, the members are not really following the local stiffness matrix, meaning well, you have diagonal member, you have horizontal member, you have vertical members, you have all kinds of members. So we have to have a certain rule, certain guidelines, global directions for axis, global coordinate system that we can represent all these members. So how can I represent this? Basically, we're saying that the truss itself is composed of members that they can go in different directions. So the displacements along the local axis doesn't mean much. I need to know what the displacement is in the global format, because the displacement of this member that goes in this direction is different than that member that goes in the other direction. So in that case, I need to transform all the displacements from the local coordinates to the global coordinates. And I also would like to transform all these forces that's been developed to the member forces in global coordinates. And that will require us to find out what is the relationship between local and global. So let's look at this member right here. That member right here, along the member x prime and y prime, these are called the local coordinate system. The other x and the y, horizontal and vertical, that is called the global stiffness matrix, or rather global coordinate system. So how do we move that stiffness matrix that we developed earlier from local to global coordinates? That's exactly what we're looking for. You are going to use the transformation matrix. So let me go back to one slide. You are going to be using displacement transformation matrix and force transformation matrix in order for us to figure this out. So in order for us to do that, we need to identify something called lambda x and lambda y. Lambda x is cosine theta x, and lambda y is cosine theta y. That is basically the inclination of every member. So if it's a horizontal member, it will have 0 angle with the horizontal, 90-degree angle with the vertical. If it's inclined as such, it will have theta x and it will have theta y. Let's see how are we going to use this. Lambda x is cosine theta x, which is x far minus x near. So it's going to be x far minus x near. Divide that by the actual length of the member. Using the Pythagorean theorem, is going to be square root of the difference of x to the power of 2 and difference of y to the power of 2. Same thing with lambda y, which is cosine theta y. In that case, knowing that displacement transformation matrix is our target right now, we would like to have the global coordinates. Each end of the member can have actually 2 degrees of freedom. What does that mean? In general, if you have any member, that can go horizontally and it can go vertically. So I do have 2 degrees of freedom for the global coordinate system. So any joint n, which is the near, or any joint f, which is the far, will have dx, or what we call it dnx, which is right there, and dy, which is dny. That's for the near. For the far end, it will have d far x and d far y. The transformation between the small d and the big D, what do I mean by the small d and big D? The small d is nothing but the local displacement, and the big D is nothing but the global displacement. It's governed by this equation. So this equation is basically giving you the relationship between local displacements and global displacement, as you can see right there. If you'd like to put it in a matrix format, here we go. The vector of the local transformation, local displacement, and the vector of the global displacement being controlled with that relationship of the transformation matrix. So this transformation matrix, which is 2 by 4, that has lambda x, lambda y, 0, 0, and 0, 0, lambda x, lambda y, is used to transform the displacement from local coordinate system into global coordinate system. And that is what we have, d equals t, or the transformation matrix times d. So what was the first step of what we discussed earlier? Number one is getting the stiffness matrix in the local coordinate system. Number two is to find the transformation matrix for displacement. What do you think number three is going to be? Transforming the forces as well from local to global. So we use that, the force transformation matrix, which is a relationship between the big Q, which is for global forces, and the small q, which is the local forces. That again will be governed by these equations. Let's put it in a matrix format. When we put it in matrix format, this is what we have. The left-hand side in this equation, keep remembering that, is going to be the force in global coordinate system. In the previous example, we have the left-hand side is the local displacement. Here we have the global forces in the left-hand side, and the right-hand side will have the local forces. What is governing the relationship between the global forces of the element and the local forces? That stiffness matrix, which is lambda x 0, lambda y 0, 0 lambda x, 0 lambda y. What is the dimension of this? 4 by 2. Do we notice anything about this matrix compared to the one that we had earlier? Let me switch back and see what we had earlier. That was T, then this will be the transpose of this. So the transpose of that stiffness, or rather the transformation matrix, is what we have here. So the big Q is T transpose multiplied by Q. So this is the third step. Step number one, we find the stiffness matrix in the local coordinates. Step number two is we got the transformation from local coordinate system to global coordinate system in displacement. Step number three is we got this transformation for forces from local to global as well. What is our ultimate objective? Our ultimate objective is to find the stiffness matrix in global coordinate system, and this is what we are going to do in a second. We just need to keep in mind that the force transformation matrix transpose that we had earlier is basically 4 by 2 versus the first one was 2 by 4. If we write this equation, in this case, the one that we had earlier, that will give you that Q equals K prime T multiplied by the displacement D. So that is what we have. So we are going to have this equation, and we are going to have that one right here, which is Q, small q equals K prime T multiplied by D. And then if you'd like to substitute that, you will find out that the final result is the big Q, which is the global force, is T transpose K prime times T multiplied by the displacement. So these three terms in the middle is giving us a relationship between force in the left-hand side and displacement in the right-hand side. What is that entity that is giving us relationship between forces and displacements? That relationship is nothing but the stiffness matrix. So the stiffness matrix K is T transpose K prime multiplied by T. Do we have those? Yes, we have this, like 4 by 2, which has the lambdas, and you have that one, which is a T, 2 by 4 matrix that has the lambdas, and then you have the K prime, which is a local stiffness matrix. When you plug them here we go. This is what you've got as far as the transpose. This is T sub T or A sub T, which is a transformation matrix transpose, and this one is the transformation matrix, and the one in the middle with the AE over L is the local stiffness matrix. When you multiply it, you come up with this 4 by 4 matrix, which is very important, that is giving us the stiffness matrix of the member. It's a very tedious process and very lengthy, as you can see, but the good news is you don't have to do that in the test or in the homework. You don't have to develop any of these 3-4 steps that we mentioned earlier. All you need to do is print out this last equation or this last matrix that we're having, and that is the stiffness matrix in global coordinate system. That's the good news. So I don't care much about the local stiffness matrix initially and the transformation in displacement and the transformation of forces and then grouping everything together. I care about the ultimate goal. The ultimate goal is we found out for any truss member like Matthews Bridge truss, you isolate that truss and you say this truss member has a global stiffness matrix that looks as such. What do you see here? What does that depend on? It depends on the orientation. Lambda x, which is L, is the same as lambda x, and lambda y, which is L sub y. And it depends on cross-sectional area A, depends on E, which is modulus of elasticity, depends on the length of that member. All these entities are determining the stiffness matrix in a global format. Does that depend on the loading? No. So this is a stiffness matrix, which is a capacity, just saying this is a stiffness matrix that's inherited in that member due to its cross-sectional area, the materials, the length, and the orientation. These are the 4 things that we're having. So this is the most important thing that you're having for that member. So what do you think the next step is? The next step that you got that stiffness matrix of a member in a global coordinate system. But do we only have one member in truss? We have so many, hundreds or thousands of members. So all you need to do is let the computer just like add them up, all of them, to find out the stiffness matrix of the whole entire structure. So the process that we went through actually is telling you how the computer thinks. You enter everything. They start with the first step of identifying the local stiffness matrix. They go to the second step, which is a transformation of displacement. They go to the third step, which is a transformation of forces. They go to the fourth step, which is global stiffness matrix. And that is finally the stiffness matrix in a global coordinate. And I rewrite that down as such, which is K equals AE over L times this. This is 4 by 4. And we wrote down at the top what we see important, that this column pertains to n sub x. And this is the second column, n sub y. And this is fx, fy. What does that mean? The near, and this is the near in x and y. And this is the far, and the far in x and y, as you can see right here. Again, it's a square matrix. The diagonals are positive, and the stiffness matrix are independent of the load, meaning it does not depend on the load. It depends only on this inherent feature or characteristics of the member of cross-sectional area and modulus of elasticity or material type and the length and the orientation, as you can see. I hope this is good for you guys and you understand this member stiffness matrix. So now, once we have the member stiffness matrix in global coordinate system, life will be good, because what we need to do is assemble all the stiffness matrix for all those members to come up with a global stiffness matrix for the whole entire structure. This is, again, the goal for us to find out the global stiffness matrix for the whole entire structures. And then we can solve it by using something called partitioning, and we're going to be discussing this partitioning in a little bit. How can we put the order of this stiffness matrix? How can we designate the rows and columns of the matrix? We are going to talk about that, and what do we mean by degrees of freedom that the structure can go in the x and y and all this stuff. So we're saying that we are going to have some numbers. So every node will move x and y. So 1 and 2. The other node will move x and y. So it's going to be 3 and 4, and so on. So you keep going throughout all the nodes of the structure. When you put that, we're saying that the highest code number is assigned to the number of degrees of freedom. So I'm going to show you that in an example because it's a very tedious process, but once you get used to it, it will be so easy. For instance, this truss that you're having here, that's composed of 2 members only. With actual structure analysis course, you are not going to be able to find the deformation here. Here we'll be able to find deformation. You will be able to find the support reactions, and there are 4 support reactions right here, and you will be able to find the member forces and everything. We identify the degrees of freedom. For instance, at this node, it is free to go in 1 and 2, x and y. And this one is 3 and 4, although there will be 0 later on because it's a pin or fixed pin support or fixed support. But we are going to say it has 3 and 4, and that node has 5 and 6. So we have this 6 degrees of freedom. We have 3 nodes, and every node has 2 degrees of freedom. So in total, we have 6 degrees of freedom. Some of them are unknown, which is 1 and 2. We don't know how much deformation we'll have in the x and y here. And 4 of them are known, which are 3 and 4, and 5, 6. They are known to be 0. So we have unknown and we have known degrees of freedom. We are going to partition our stiffness matrix to facilitate solving the problem. So we're going to have K times deformation equal forces, as you can see right here. And some of this, let's say that known forces at this location. I have 0 force in the x, and I have negative force in the y. So I have these 2 in red color. These are known forces. Equals to R1 and R2, which is unknown displacements, multiplied by whatever you have here. When you solve this as sub-matrix, like you partition the matrix and you solve them, knowing the forces, you can find out this displacement. That's step number 1 in the answer. Step number 2 is finding this displacement. We will be able to find the reaction forces. And step number 3 is going to be finding the member forces. Let's see what we're talking about. So the fundamental procedure here is calculate the stiffness matrix as we've seen before. We are not going to go through this test, but this is a local, this is a transformation, and you come up with the global stiffness matrix. Assemble all the stiffness matrix for the members in global coordinate system, and then start solving that problem. So the last thing I want to point out is there's something called member forces. What do I mean by that? We were able to find displacements. We were able to find reaction forces, but we didn't talk about the internal forces in the members. You follow this equation, which is small q equals k prime t, which is a transformation matrix, times d, which is the global displacement, and that is going to give you that force in that member. So basically, that blue color box is the one that you are responsible for, that you find this force. If it is negative, that means it's in compression. If it is positive, that means it is in tension. So this is what we are going to be using, and we come back to it. We are going to go through some examples. One of them is basically composed of 2 members, and we are going to be discussing that in a few minutes. And this is the end of today's lecture. The next lecture, we're going to be discussing several examples in order for us to solve this together. Thank you so much, and I'll see you guys next time. Thank you.